in the previous class, which was probably like a week ago, right? We had an exam and the exam review after that. I believe we started to talk about the last topic of this semester. Well, that's actually a lie. Probably I'm going to have another topic, okay? Neural nets probably is not going to take us more than a couple of classes. And then after that, I'm planning to show you actually kind of why do we even build all these things, right? I mean, how do we compare? We discussed a lot of different models. So let me bring that up, actually. If I can find it, this, right? Tools matrix, right there, okay? Remember, I gave you this handout, right? That's actually everything that we learned in class so far. At the beginning of class, if you remember, we discussed classification trees, right? And then we said, if your target is numerical, then it becomes a regression tree, right? So you're predicting numbers, but using a decision tree structure for that. Then we said, well, if you also are predicting numbers, another way to do it would be multiple regression, right? And you did the project when you predicted the movie success. By the way, I'm almost done grading the projects, okay? And I'm posting the grades as soon as I grade them. So if you check out the Google Doc that you shared with me, if nothing is there, no comments, that means I didn't get to that yet. So I'm almost done, okay? So be patient a little bit. So you did the multiple regression to predict the movie performance in terms of the box office based on a bunch of variables, right? Based on the budget, based on the genre of the movie, whether or not it has major movie stars, etc., etc. And it can be used if your predictors are both continuous or categorical or a mixture of them, right? And then we also discussed logistic regression, right? And logistic regression really is classification, right? At the end of the day, you want to classify each observation in your data set as 0, 1, yes, no, male, female, default on the loan versus normal loan, survive, die, drop out of college versus stay in college, right? Leave the company versus stay in company, so that kind of problems, okay? Now, what's not on our tools matrix is clustering, right? Remember we did clustering, and clustering actually belongs to the unsupervised learning, right? Because you don't predict anything in clustering. You don't predict numbers, or you don't predict categories, you just say, let's group similar records together, okay? So let's actually add clustering into our unsupervised column, okay? And we looked at two different ways to cluster, right? We looked at, how did we call the first one? When you start with like all points is the single cluster of one until everything is one big cluster that contains every single point. That was called hierarchical, right? So let's add hierarchical clustering, okay? And also, what was another way? When you know how many clusters you want from the get-go. K-means, right? So K-means, right? And these clustering methods actually are good in both cases when you're... So here it's actually a little bit misleading because it says predictors, right? We don't have predictors. There is nothing to predict. It's grouping of similar records. That's all there is to that, okay? So you may be grouping your variables. Actually, it can be done, like the only thing that we did in our examples in class was grouping records when we used only category, only continuous columns, right? Remember, we looked at cereals, for example, right? Cereals, we measured in each cereal content of fiber, carbohydrates, fats, etc., etc. Every one of them was a number, right? What if we added more columns? Like, for example, cereal can be hot, right? Served hot when you microwave it, or served cold when we just add the milk and that's it, right? Can that be also part of our data set, such column? Yeah, of course, right? You have to still figure out how to kind of use numerical columns and non-numerical columns together, right? But it can be done. So therefore, hierarchical clustering, as well as k-means, actually is applicable when you're grouping things based on continuous columns and also based on categorical columns, right? So we didn't discuss that actually in class because I didn't want to obscure the picture, which was already obscure even without it, right? But you can have all kinds of columns, categorical or numerical, continuous columns, and still should be able to group records, group them together, okay? So that was something that we did before. Unsupervised learning, the only thing that we discussed was clustering, k-means, and hierarchical. So today we're going to actually discuss really cool and really popular data analytics technique. Okay, that's actually what why this area is called machine learning. Okay, the neural net, which we're going to discuss, well, in more or less details today, is probably the hottest topic right now. Okay, what can it do? What can't it do? All right, it can do anything. So let me put that into our metrics. Okay, first of all, neural networks can be used, oopsie, looks smaller, right? It can be used if your target is a categorical variable, and your predictors can be either continuous or categorical. So it can fit actually in any of these two categories, okay? So first, let me start by saying this is a supervised learning method, okay? So there is a target column, right? You are trying to predict something using the neural nets, okay? So whatever you're trying to predict can be categorical, yes, no, right? In fact, the example that we're going to take a look at today predicts exactly that, right? Or, same thing can happen if you're predicting numerical target, okay? So continuous target if your predictors are continuous, or your predictors can be categorical. So you see that? Neural nets actually fit everywhere, okay? So all these different models that we considered in the class, they can address only specific certain type of target, right? So most of our models that we considered, they're good only if you have continuous target or you have categorical target, right? You have multiple regression if it's continuous. You have logistic regression if it's categorical. Neural networks can do anything really. Okay, very powerful, truly accurate model. That's the upside. Okay, you know what's the downside? It's so mysterious. Like for example, you remember how when you ran the multiple regression, I asked you, can you interpret the slope, right? And you would tell me, yes, if independent variable is increased by 1, that's the amount of increase in the target, right? Like for example, in your projects, you told me that slope for the budget 0.70 or something like 0.69, right? What does that mean? For every extra dollar that we put in the budget, the box office goes up by 69 cents, right? Very clean, very straightforward interpretation, right? Well, neural nets don't have anything even remotely like that, okay? Neural nets, for the lack of better explanation, is a black box, sort of, right? It has input coming in, output coming out, and what happens inside, it's a big black mystery, okay? So it's highly uninterpretable model. We just have to, sit back and look amazed at how greatly it performs classifying target or predicting our numbers, right? So, and it does actually predict in a lot of cases very closely to what your data set is, okay? So really powerful, but very poor in terms of interpretation. So let's kind of, now that we got this out of the way, let's start the discussion, right? Okay, neural nets. And I posted these slides, by the way. You will see one slide that took me last semester 3 hours to put together, okay? But you will see if it's worth it or not, okay? So we discussed that neural net is really an attempt to model human brain, right? We said that human brain contains how many cells? I told you, I believe. About 10 to the power of, remember? 10 to the power of 10 neurons. And each neuron looks like that, okay? So neuron, oopsie, it has, let's go back. It has the nucleus that does, I guess, the processing, right? And it has, what are you going to do with this? All right, and it has kind of a tree structure around that, right? So there are a lot of dendrites. These are like nerve endings, right? They all converge into the nucleus, and there is one outgoing axon. So dendrites carry signals into the cell. axon carries signals out of the cell. And what happens is other cells, okay, they have also dendrites and axons, right? So other cells, axons, they contact the dendrites of these cells specifically. So every time when other cells want to communicate with that cell, it just basically releases the chemicals like messengers, right? They're called, I believe, neurotransmitters in the brain, and there are certain groups of neurotransmitters, right? Actually, brain, I believe, is governed by mostly 3 neurotransmitters. One of them is called serotonin. Have you heard about that? Serotonin? Serotonin is calming neurotransmitter, right? So it makes you like peaceful, right? Then there is norepinephrine. Norepinephrine is actually the effect of coffee, right? When you want to stay awake, you take you drink coffee, and coffee basically creates a wave of norepinephrine inside your brain. Okay, norepinephrine is excitatory neurotransmitter, so it basically makes the brain to concentrate, make it aware of what's happening, right? And there is also dopamine. Dopamine is also kind of excitatory neurotransmitter, but it's a reward center, right? So people who do drugs, that's basically what they get, right? So when they inject like heroin or something like that, it creates a wave of dopamine in the brain, okay? That's why they feel so euphoric, okay? So all of that has actually neurochemistry behind that, okay? And all the psychological disorders are explained by imbalance of chemicals in the brain. Like, for example, schizophrenia. It's well known that schizophrenia, when people hear voices and see weird things, right? It's basically excessive dopamine in the brain, okay? When people go on antidepressants, which, by the way, is a bad idea, always, right? Essentially what doctors are trying to do is they're trying to raise the level of serotonin in the brain. Well, it's not really true. What they're trying to do is keep serotonin, as much serotonin in the intercellular space as much as possible. Because what happens is when the cell releases the neurotransmitter such as serotonin, it gets to the other cell, and then whatever was not attached to the other cell gets back. It's called reuptake in the brain. The process is called reuptake. Okay, so what antidepressants do is they block reuptake. So therefore, serotonin stays active in between cells. That's essentially how it works. Anyhow, so the idea basically is that the signals are converging in the center of the neuron coming from dendrites, and then nucleus of the neuron does some weird stuff which we don't know what the hell happens. If you ask any neurobiologist, 80% of the answer is going to be I don't know. Okay? Any question that you ask neurobiologist, there is an 80% chance of an answer I don't know. And that's actually true. We don't know what happens. Don't know the chemical nature of what happens in the brain. It just happens, okay? So it sums up all the signals coming in, and it says, if it's above certain threshold, I'm going to send the signal out, okay? And the signal propagates along this axon. But if the sum of the signals is not strong enough, I'm not going to send the signal out, okay? So that's basically how the brain works. It's either something or there is nothing. Weird, right? Well, but that's what it is. So here is what happened in probably 1970s, okay? Scientists had a very rational idea. They said, you can beat nature, right? If nature designs something in a certain way, that's the result of millions, if not billions of years of evolution, right? It's the best design out there. So therefore, let's not even try to create something better. So let's take the model of how the brain works, okay? And let's simply reproduce it, okay? If the brain is capable of amazing things such as learning, memorizing, abstract thinking, right? We can think of the things that we can't even imagine, such as quantum mechanics, for example, right? Weird science. Okay, so brain has certain amazing capabilities which we don't understand how they work, but let's not even try. Let's just basically model how the brain functions, okay? And that's basically simple neural net. So here's what happens, okay? These nodes are called input layers. So just like in the brain, okay, every cell receives multiple inputs from neighboring cells, right, that contact that specific cell. So we're kind of going to assume that this is my axon, sort of. It's a model of an axon, right? So this is the body of my axon. That's the nucleus of the cell. And it receives inputs from, well, outside, from somewhere, right? From other cells that contact us, okay? So in the neural net model, there is always input layer. Input layer means that it just takes the inputs, external inputs, and then it forwards them to the next layer, okay? And then there is output layer. So essentially, that's my single axon that sends the signal out, right? And the signal can be either active or zero, right? It can be 1 or 0. Well, technically it can be in between, but remember how we do the classification. We calculate the probability, and if probability greater than 0.5, what do we say? It's a 1, right? If the probability less than 0.5, what do we say? It's a 0, right? That's how we classify responses. Essentially, that's what our model is going to do. Okay, so here's basically what happens. The input layers, so these nodes 1 to k, and by the way, I may have as many inputs as I want. Okay? Typically, in the neural net, inputs are just variables. Remember that neural net is the supervised learning technique, right? Which means that we have one single target that we're trying to predict, and everything else becomes what? If it's not target, it becomes... What are other variables called? We have a target variable and a bunch of predictors, right? Predictors, right? That's what we use to predict the target, okay? So that actually, how many input nodes do I have? As many as I have predictors, right? So for example, my file contains, let's say, 25 variables, and one of them is my target. That means I have 24 predictors, right? So I'm going to have 24 input nodes in my input layer, okay? So what happens after that, the input nodes really don't do any processing, okay? What they do is they receive the signal and they pass it forward. So there is nothing going on at the input layers, okay, at these nodes. So if value x1 comes in, the value x1 comes out. Input layer is just kind of a messenger guy, right? So I receive a signal, I pass it forward, no changes, okay? Then what happens is, in order to model the brain, some connections, some of these layers, what did I say, layers? No. Some of these links between the input layers and the body of my cell can be more important than others. It can happen, right? Like, for example, let's go back to this model of nucleus, right? Of the neuron. So, for example, this signal comes in from another neighboring cell, but cell decides that this signal is going to be not processed. So we're not going to pay much attention to this signal, right? So it's going to be a weak influence, right? We can do the same thing here. In what way? Well, we multiply the signals that are coming in, x1, x2, xk, by their weights. So w1, w2, wk are the weights. Numbers that are attached to every incoming signal, okay? And then after that, we also add on the top of that certain constant. So we call it theta 1. Okay, so essentially, here's what happens. I got a new pen, by the way, so let's test it out, right? Let's test out the new pen. Node, right? Oh, I can't find it. Okay, maybe next time. So what happens is my signals essentially are getting multiplied by the weights, and I'm adding the constant to that. And that's going to be my incoming signal into this output layer, right? So essentially, what I'm doing is I'm creating a linear combination of my variables. Very much like linear regression. So in other words, you can think of that as theta 1 is your intercept. Remember what we did in the linear regression? We did the intercept. Plus beta 1 x1, beta 2 x2, right? Same exact thing, okay? When inputs are coming in, they're being multiplied by the slope, so you can think of these guys as slopes, right? And that one is an intercept. So we create like a linear combination. And then after that, this node right there, okay, applies certain function. It's called transfer function or activation function also, okay? So in other words, it says, let's take an input and convert that into the output using certain rule. That's all there is to it. So essentially, neural network is just a bunch of mathematical formulas that are hooked up with each other, okay? So let me actually illustrate that. I think it's going to be better if I do the illustration. Because even I have a feeling that it's just a bunch of, what the hell is that, right? What are you talking about, man? We were confused. Okay, so let's take a look at this problem right there, okay? Again, neural net always has an input layer and always has an output layer, right? That's a given. And you can have actually as many hidden layers as you want in between. What hidden layers do, they do exactly the same thing. So let me illustrate that. For example, x1 input comes into the node number 1. Node 1, we discussed that doesn't do anything with it, right? It just says x1 is received, I'm sending x1 forward, no modifications. So after that, every one of these nodes in the hidden layer receives x1 multiplied by a certain way, right? And then with x2 happens the same thing. So all the signals converge over here, and it does some transformation to the signals, it creates the output. And after that, all the outputs from all these nodes come forward to the next hidden layer, and they're getting processed again, okay? And then outputs from these nodes come together in this node, they're getting summarized and converted, and that creates an output. So it's kind of a weird structure, right? We send the signals in the incoming node, and they being processed, converted, move forward, getting processed and converted again. So it's basically every signal is getting converted multiple times, and then it spits out the result. You see how screwed up this structure is? It's virtually uninterpretable. Whatever happens inside, we don't know. It's just a bunch of signals getting modified. That's all there is to it, okay? So very complicated model, really. And there is not much good interpretation at all. Turns out really powerful, okay? So let me give you a couple of examples how that thing can work. How many of you on your cell phones have camera? That's a stupid question, right? Everybody, basically. How many of you have this yellow square? When you point to the group of people, it can tell where the face is. That's neural network in action, okay? So it can take an image, analyze pixel by pixel, and find the group of pixels that looks like a face, okay? So it's really neural network. How many of you have Siri on your iPhone? Siri can recognize the voice, right? Same exact thing. Program can recognize handwriting. So you write something, and then it compares it against well-known patterns that it understands and makes a determination. Is it an A, or is it an O, or is it a 6, right? So image recognition. I told you before that probably medical field is going to get changed in the future, right? And one of the things that is going to go away would be radiology, right? We discussed it. What radiologists, what they do is they can work from home, right? Patient comes in, they do the MRI or X-ray, and they just basically upload the images, pictures into the system. Radiologist logs into the system, looks at the images, and then uses his judgment, really, right? They're looking at the picture of, I don't know, a liver, right? And they say, well, that thing looks weird to me, so it may be a node, or it may be a fatty liver, or whatever it is, right? So they use their judgment based on their training, right? They can get tired, they can get, drowsy, right? Things can look blurry, obscure on the images. Well, we can train software using the neural net to actually look at the pictures, analyze it frame by frame, pixel by pixel, and look for certain patterns, right? Let me give you another example. How many of you are planning to take GMAT? GMAT is the test for MBA, right? Part of the GMAT, or any other online testing, is writing a survey, right? So when you type, like they give you a topic, right? You type something on your computer. Who grades that stuff? Somebody needs to read that, right? And give you a grade. So who does that? What do you think? Well, the obvious answer is English people who are employed by educational testing services, right? To read thousands and thousands of surveys and grade them, okay? Yeah, that's how it used to be, okay? But since then, what happened is they trained neural network to be able to scan. Literally, it's kind of what known actually in the data analytics, a bag of words, quite literally, okay? There is a branch of data analytics. Geez, I really get distracted today. It's like going on tangents, right? Another branch of data analytics is actually text recognition, text mining, okay? For example, I don't know if you know or not, but your Gmail account has spam folder in it. Do you ever touch spam folder yourself? No, you don't even look at that, right? But if you click on the spam folder, there's going to be all kinds of crap inside, right? Some, timeshare offers, right? Some, jewelry or whatever, right? So some weird stuff, okay? Who does the filtering? Filtering is done by the software, really, right? And the software spam filters, that's how they work. Every incoming message is getting broken down into words, right? So that's why this method is called a bag of words. So it's literally like a bunch of words. Now, of course, we have to discount certain words, right? Such as the, a, of, in, because they don't have a meaning, right? By themselves. But other words, we have to look at them. And after that, basically, there are rules that were programmed in the software, right? How do you recognize the spam message versus legitimate message? Well, they have to analyze the words and groupings of words, right? And then, after that, make a judgment. And again, it's a classification problem, right? Is it a spam or is it regular message? It's kind of 0-1 kind of classification, based on the what's inside the bag of words. Anyhow, let's take a look at this problem right there, okay? I don't know if we have time for that today, so maybe I'll just introduce it today. And then we'll do it on Friday. So it's the end of the semester, we're taking it slowly, right? Kind of taking it easy, chilling. All right, anyhow, let's say it's a cheese tasting contest, okay? So you go to the, cheese fair. Are there cheese fairs out there? Could be, right? Yeah. So, or you go into the store, right, and they have a bunch of cheeses for you to taste, like little samples, okay? So you taste the cheese, little sample, and you say, I like it. And some of them you say, yucky, right? And basically what we want to do is build a model that will allow us to predict whether or not a customer will find the cheese tasty or gross, right? So like versus dislike. And there are two things that we can manipulate about cheese. Fat content, fat score, right? I don't know what that number means. Maybe grams of fat per serving or something like that, right? 0.2, 0.1, you can see that we have a range, right? And also salt score. So here is really not salty cheese, right? Versus this one is really salty, okay? So what we'd like to do is being able to train the model, neural net, such that what we have to throw inside the neural net is these two numbers, okay? Every cheese we can measure how much fat inside one serving, right? What's the fat content and what's the salt concentration. And after that, we can throw that into the model, and the model will tell us if that cheese is going to be perceived as, I like it versus no, I don't like it, okay? All right, so here's the idea. Bam. And that slide, next slide, I believe, took me enormous amount of time to put together, okay? So we're going to use this simple neural net. So as I was telling you, no matter how many how do we call layers in between, kind of in the middle? We call them, start with H. Hidden layers, right? Hidden layers. But no matter how many hidden layers you have in between, you have to have input and you have to have output, right? No matter what. So our input has two nodes, right? Because we're going to decide whether or not cheese tastes good based on two inputs, right? It's how much fat is in serving and how much salt is in serving. So there are two nodes in the input layer. And here we're going to actually assume that there are two outputs. Now, two output nodes, that's a little bit weird, right? What we're trying to predict is this one, right here, okay? This column, acceptance. Whether you like that thing or not like that thing, right? So there should be one output, right? But we can actually have more than one output node in the output layer. And in this case, it can be done by, in different ways. For example, let's say my output node number 6 says that the score of this cheese is 0.75, right? Which means that people probably are going to like it, right? The other output says that the score is 0.4, for example. So what do? One output says it's a yes, another output says it's a no, right? Well, I can do a couple of things. I can do average, right? 0.75 plus 0.4 divided by 2 gives me 525. Then it's a yes, right? So based on average. Or I can say whatever the voting is, right? So these are kind of votes, right? Two outputs, okay? I take the highest, for example, or I take the lowest. So there are more than one way to try and model that, okay? So as I was telling you, each connection between the nodes has the weight, right? A number. Okay, so between node 1 and 3, I have W13. Between node 1 and 4, W14. So how many connections I have, that's how many weights I'm going to have, right? So this one, for example, between node 3 and 6, node 3 and 7, W36 and W37. These are numbers, more like slopes, right? Analogous to slopes, okay? And then, of course, every node has also some fixed number, right? So we create linear combination of inputs and then add a constant to that. So these numbers, W's, they act like slopes. The theta 3, theta 4, theta 5, and theta 6 and theta 7, they act like vertical intercept, right? So, all right. So let's do that, okay? Oh yeah, and another thing. Man, there are too many moving parts in this model, right? Remember what I told you is the signals converge, right? We multiply them by the weights, we add the intercept theta, and that's what happens. What happens is we have to process the signal, right? We have to take all these outputs and convert them, all these inputs and convert them into the output, right? So there should be a transfer function or activation function, it's also called, okay? In general, there are multiple types of activation functions, okay? It can be linear function, so I just say these inputs, W13 times fat plus W23 times salt plus theta 3, that's what my output is going to be. So I'm not going to do anything with it, okay? Just combine these inputs and pass them forward. It's a linear function, right? Or it can be another popular way how the function is modeled is sigmoid. Remember we discussed sigmoid functions? Like logistic function is sigmoid, right? Because it has the shape of an S, right? This elongated, really flattened out S, okay? Or it can be Gaussian function. So whatever we do at node 3, that's basically how we process the signal, okay? Now I don't know if we should start that or not, but let's at least try. Okay, so here goes. Okay, suppose, yeah, there you go. Suppose I have these inputs coming in, right? So I have 0, 2, fat. So certain cheese, right? I'm trying to predict whether or not people will find it tasty, right? So fat content 0, 2 and salt content 0, 9. And these are the weights that I'm giving. 0.5 minus 0.1. Weights can be negative, positive, I don't know, right? Whatever works, that's what works. So, and also I do have some intercepts, right? Minus 0.3, that's my theta 3 for the node 3. 0.02 for the node 4, etc. Okay, so this is what took me so long, all right? That's 3 hours of my life, basically. Okay, cool. So first things first, what input nodes do is they don't do anything with the inputs, right? They just take the input and pass it forward, right? So 0.2 on node 1 becomes 0.2 after node 1, right? So node 1 doesn't do anything. Node 2, same thing. 0.9 comes in, 0.9 gets out, okay? Then after that, these inputs have to be sent to which nodes? 3, 4, and 5, right? And not only we just send them, we multiply them by the weights, right? So we combine them in a linear fashion. Look at that. 0.2 is getting multiplied by 0.5, right? And then from what happens from node 2? What do we multiply it by? You tell me. When it comes to node 3 from node 2, what do we multiplying that by? 0.01, right? Multiplied by 0.9. And then on the top of that, we add minus 0.3, right? Because it's like a free term, a constant that sits at node 3. So all these things are getting added together, just like that. Okay? Do you see why it took me so long? And that becomes the input into node 3. Whatever the result is, minus 0.281. And after that, I have to convert that, right? So I apply the activation function. And let's say that we're using this one, logistic activation function, right? We discussed that function when we discussed the logistic regression, right? So, therefore, what I have to do really is to take 1 divided by 1 plus e to the minus that power. That's how I convert my signal, right? And the answer is 0.43. And that becomes an output from node 3. You see how it works? Signals come together into the node. Node says, here's the function, let's just do it. Converts it into another number and spits it out. Okay? Do you see how confusing that can get? What's the interpretation of the slope? 0.03, point blah, blah, blah. There is no interpretation, right? Just a bunch of numbers inside the model that getting multiplied by all the signals and then they're getting converted. There is no interpretation, right? It's literally a black box. Like we throw the signal inside of that, it goes through all this scrambling and then gets out. And whatever it is, we have to say, yep, it's a go or it's a no-go. Weirdest model in the world, right? With no good interpretation, but amazingly accurate. Okay? So same thing happens with node 4, right? So you tell me, what my signal out of node 1 is get multiplied by when it comes to node 4? What's the multiplication weight? Negative 0.01, right? So 0.2 times negative 0.01. What happens with node 2 from 204 to node 4? 0.03, right? And then they combine together, including the free term, right? 0.02. Kaboom. And that's the input into node 4, right? 0.004, that's what comes into node 4. And then we apply the same activation function, logistic regression. It gets converted into 0.511, right? By this weird mathematical formula. Bam. That's the output from my node 4, okay? And then for node 5, same thing happens. I take input 0.2 multiplied by the weight 0.2. I take 0.9 multiplied by minus 0.01. That gets together with 0.05 equals to 0.081. That's input that comes into the node 5, right? And then apply the activation function, it becomes 0.52. That's an output from node 5. Okay? See what happened? What happened is my signals that I first sent in, 0.02 and 0.9, were kind of modified. They filtered through my hidden layer, right? By doing all this mathematical mumbo jumbo, and these signals became 0.43, 0.51, and 0.052. Same exact thing will happen on the next step. So let's watch that thing, right? So first things first, I take the output from 3, 4, and 5, and let's do the node 6 now, right? Multiply by minus 0.02. That's from node 3. From node 4, I multiplied by minus 0.03, and from node 5, minus 0.02. They converge together, and the free term, the constant is minus 0.04, right? So that's the combination equals to minus 0.07435. That's the input into node 6, right? That's what comes into node 6. What comes out, I have to apply the logistic transformation, right? Bam, it becomes 0.48. So that's the output from node 6, okay? Let's take a look at node number 7. Same thing, right? 0.43 times what? 0.01, right? 0.511 times 0.05, right? And 0.52 times the last one, 0.015. They converge together and multiplied and add with this point, whatever it is, 0.015, blah, 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 right? And that becomes an input into my node 7. And then I again apply the logistic function, and it gets out as 0.056, right? So there you go. So my signal, content of salt and content of fat, they were transformed in a weird, wackadoodle way, right? And it became 0.481 and 0.506. So I have two predictions, right? So what do I do? Again, with what we discussed, I can find the average between them. And the average is going to be, oh gosh, probably something like 0.49, I'm guessing. Average between them, right? So if the response is 0.49, what do I do? Is it a yes or is it a no? It's a no, right? It's below 0.5, right? That's one way to do it. Or I say, well, I'm going to take the highest of the votes, right? And highest would be 0.506. In this case, it becomes a yes, right? So depending on how I pick, the voting schema, right? I will get a different answer. And all that matters really is, will I be able to predict my training? And again, same thing, right? There is a training set and there is a validation set, there is a testing set, right? This model actually, what's good for neural networks is the more data you throw into the neural networks, the better it becomes, okay? So the volume of the data is really critical. The more examples with answers, right? So here is the cheese that we found tasty. 0.02, 0.05, right? So you give it more data, it becomes more sophisticated. The model trains really, it feeds on the data. Okay? So therefore, for neural nets, it's kind of, that's why it's called artificial intelligence, right? It learns, the more data you throw at it, the more it learns, the more accurately it predicts the output. Uh-huh. Yeah, we predict what score a person would give to that cheese, right? With 0.9, 0.2, and 0.9, right? So that's why it's called artificial intelligence, because it really learns by adjusting. By the way, learning, last thing that I want to emphasize, right? What do we mean by learning, right? What in the hell do you mean by learning, Prof? So here's what we mean by learning, okay? These weights, 0.05 minus 0.09, and this constant, 0.03, 0.002, right? That's what basically manages how the signals converge, how the signals get inputted, like coming into the layer, right? So when we say train the neural net, what we mean is all these coefficients, all these constant terms, the slopes, etc., they have to be moved around, right? So the model basically, it learns in iterations, right? It starts with certain numbers, certain slopes and certain intercepts, and it says, let's see if we can predict the actual data. So there is a data about people liking or not liking cheese, right? So we do the first pass, and every time when we do the mismatch, so we predicted that they will like it, but actually they didn't, oopsie daisy, we have to make an adjustment, right? So therefore we move slightly these coefficients, right? And then we do it again. We see if we are close, right? And it goes in iteration until we basically find the combination of these numbers such that we can predict closely. That's what it means to train neural net. Really, it's just to modify all these numbers so that you can predict accurately what happened in your data. Really weird concept, right? But works really nicely. Go figure, okay? All right, we're done for today.